We continue our team on multi-object tracking. Risi Kondor from UCL Gatsby Neuroscience Unit, and he will be talking about Fourier representations of the symmetric group for multi-object tracking.
Great, thank you very much. Right. So I think this talk actually fits quite well in this workshop because several of the previous speakers have also talked about multi-object tracking and the various problems that gives rise to. But maybe I'll concentrate on a slightly different aspect of the same problem, because what I'll be talking about is what is called identity management problem. So essentially the problem of maintaining a distribution over assignments between the objects and between the tracks that you are maintaining in your system. Okay. And I'm going to propose a particular algebraic framework to do this based on harmonic analysis, so Fourier analysis, but not the usual type of Fourier analysis, but this non-commutative fancy Fourier analysis on groups, in particular, in this case, on the group of permutations. Okay, so this is joint work with Andrew Howard and Tony Jabara, who are at Columbia, where I was until very recently, where I finished my PhD, and this is part of that work. Great. I'm actually going to be using the board. You must tell me when you can't read my writing or you can't see the board or any of those. And please interrupt me frequently. Okay. So again, this is the problem I'm dealing with. Originally, it was mostly came up in the context of radar tracking, but now it has become more general. Just you have multiple objects in your world, you receive these blips of their position or approximate position through time, and you not only want to approximate their position, you also want to keep track of who is who. So in this case, for example, you want to know whether this is what really happened. So these two, say, planes came close to each other, but then they got scared of each other and went in opposite directions, or whether they actually crossed. It is not obvious from the data itself, but you also have some information, some observations of the identity. So you're going to be updating your model of your filtering system based on both the position information and these identity informations as they come in. Okay. So obviously this gets worse when there are more particles. For 2 or 3, you can maintain an explicit distribution over all the n factorial possibilities, but really my talk is going to be aimed at the sort of regime where you can't do that anymore. So say you have 20 or 30 or even more different objects which you are tracking. Obviously you can't maintain information about 30 factorial or n factorial different permutations in your computer. Okay, so as I said, the origins of this subject are mostly in radar tracking, but it's not just about radar tracking at the moment, thank God. It turns out that this has become an interesting problem for all sorts of different reasons. Partly sensor networks, which are becoming more and more ubiquitous. Then it also comes up in contexts like vision, where you're maintaining landmarks. So you get a video of somebody, and you want to individually track the eyes or certain other landmarks that you see on the image, and you don't want them to get mixed up. Motion capture, when you are dealing with human bodies or bodies of animals, again you are maintaining these individual points. You have uncertainty about their position, but also about their identity. And as one of the previous speakers mentioned, in biology, ecology, when you're looking at stuff under the microscope or out in the wild, you also have this sort of issue of tracking multiple things and worrying about their identity. So this is becoming more and more of a theme on the applied side. Now, this is one diagram that you've seen before several times. So hidden Markov models, of course, this thing eventually translates into some kind of hidden Markov model. Except that in my case, we were focusing not just on the hidden Markov model of positions, so x1 up to xn, but we also have to worry about this hidden permutation. So sigma permutations are going to be denoted by sigma in this talk, and we're also propagating that around along our chain. And then the observations also relate to sigma, but they might not reveal the entire permutation. They might just give information about parts of it. So you might just observe that one of the aircraft in the radar case reports that I'm here or something like that, or several of them. or you have other sorts of information, other constraints that come in. You want to propagate this information in this sort of filtering way that several of the other previous speakers have talked about. Okay, so there is a hidden Markov model, there is filtering, there's this online Bayesian kind of approximation thing that we're trying to do. In that respect, the context of my talk is similar to what others have talked about. What is the crucial difference is that I'm really trying to focus on the combinatorial aspect, so on the permutation thing, on the matching thing, and going to try and isolate that from the problem of actually maintaining the positions. So that I'm claiming that these are two sort of different sides of the same coin, and to some degree they can be dissociated from each other. Now, another important thing is figuring out what kind of regime you are in. So, like if you are actually flying home somewhere from this workshop, hopefully you're not going to be in the regime where I'm talking about, and the radar operator will have a fairly good idea of which aircraft is which on his screen. And in that case, of course, you still have to worry about maintaining identity, but it might be okay to just maintain a few possibilities, right? So in that case, you might be propagating particles or just maintaining a few possible permutations, updating their probabilities, and so on. On the other hand, when there's lots of noise or very few observations, maybe lots of position observations, but a lot of uncertainty about their about the actual position, so huge error bars on them, or specific things happening like people behind or aircraft disappearing behind clouds or shields or whatever, you have a much more sort of smoothed out, spread out distribution over your n factorial possible permutations. And in that context, you really can't, this idea of maintaining individual possibilities, particles, really is not going to cut it, right? Because whatever you do, the number of possibilities that you have to worry about is going to blow up exponentially with time. So instead, you want distributions in the true sense over permutations. As I said at the beginning, the issue is how to maintain such a distribution when you can't afford to maintain it pointwise. So you can't afford to maintain n factorial numbers in your computer. Okay. So this is the general thing I'm going to be talking about, and this is the distinction between kind of the data association and identity management. So data association is when when you have relatively a relative wealth of identity information, whereas identity management is when you really have much sort of vaguer observations. The identity information comes in bit by bit, so it's also a kind of sort of agglomeration problem of fusing all these little bits of information about the permutation. How do you come up with a single permutation from it at the end, and so on. So that is the regime I'm going to concentrate on. All right, now how does the combinatorics, how does the math come in? Well, let me tell you a couple of general things about the sort of math I'm going to be using. So what is this business of harmonic analysis on non-commutative groups? What do I mean by that? Well, what is the usual type of harmonic analysis? It's something to do with the Fourier transforms, right? So if you have a function, say, on the real line, or maybe it's easier, in fact, if you have a function on just the numbers from 0 to n minus 1, so this is going to be discrete Fourier transform, then the Fourier transform of this function looks something like this. So it's the sum over our domain. So I is going to go from 0 to n minus 1 of the function values, so f at I, weighted by these exponential things. So something like I 2 pi k time. Oh, there's a bad problem with the notation. Two different i's in two different senses. So let's just say x. Okay. So I exponential of minus I 2 pi k x is what I have up here, even if you can't read it. There's a little note saying that whatever you write on this board might not be visible to the audience or might not be legible, so it's obviously not my fault. I think you've been warned. All right. so how do you generalize this to groups? What does it mean to generalize it to groups? So in my case, what does it mean to generalize it to permutations? It means that my original function f is a function of permutations. So the group of permutations is called the symmetric group. Symmetric group over n objects is denoted Sn, and we have a function on Sn now. Effectively, we have a distribution on Sn, and we want to do something similar. In particular, what we're aiming for is a similar sort of hierarchical decomposition of the space of functions as afforded by classical Fourier analysis. So we want to be able to talk about kind of low frequency modes and high frequency modes, because that's what's going to afford us a parsimonious representation of distributions. We are only going to focus on the kind of slow modes of this distribution and claim that the fast modes can be neglected because those are the ones that change fast anyway, and so on. But these are the inaccurate ones. Okay, so the generalization of Fourier transformation to groups takes a kind of similar form. If you write it down, it's also going to be a bunch of Fourier components which are sums over our domain. In our case, the domain is just the group, so it's just permutations. So we're summing over permutations, and we're summing the values of the function, and so f of sigma. But the question is, what goes here, right? So what is the interpretation of this exponential thing? And it turns out that what goes there is a representation of the group. Okay? And that's the fundamental difference between Fourier transformation on the real line and the classical Fourier transforms in general, commutative structures versus non-commutative structures. The fundamental distinction is that this thing is going to be a matrix, and therefore the individual Fourier components are going to be matrices. So this is this weird kind of thing, whereas in the classical case, Fourier transformation took you from a function on your domain to another function on the same domain, right? This is f hat is also indexed by just an integer in this case. Here, the Fourier transform is going to take you from a function on permutations to a bunch of matrices. But otherwise, it turns out that many of the important properties of Fourier transformation do carry through naturally. So we have things like unitarity, and therefore it's an invertible transformation. We have the convolution theorem, the translation theorem, and so on. So this is a really canonical theory within representation theory or group theory. It's a direct analog of classical Fourier transformation. And it even has its own algorithms, which we're going to exploit seriously in our applied problem of multi-object tracking. Okay, I haven't told you what representations are. This is going to be one of those things that kind of divides the audience, because if you come from a physics background, then you know what representations are. They're kind of crucial in modern physics. Some people, on the other hand, they don't necessarily feature in, say, a computer science curriculum. So I can't avoid having to tell you what it means to what these representation matrices are, what properties they're going to have. So the idea here is that we concentrate on the structure of the object, in this case the structure of permutations. In particular, we concentrate on how permutations compose, right? So the sense in which permutations form a group is that if you regard a permutation as a mapping from the numbers 1 to n to 1 to n, a bijective mapping, then permutations have a clear notion of multiplication, or the clear notion of combining permutations just by composing these maps. So if you have two permutations, sigma 1 and sigma 2, then the product of those two is defined as the map, which just corresponds to doing sigma 1 first and then sigma 2. Sigma 1, I. Okay, so this is our notion of multiplication on permutations, and with respect to this operation, permutations form a group. So in particular, the product permutation sigma 2, sigma 1 is also a permutation, obviously. Then this operation is associative, so sigma 1, sigma 2, sigma 3 is the same no matter how you bracket it. There are inverse permutations, so if you, for all sigma, there exists a sigma inverse, and there is another sigma inverse such that sigma inverse times sigma equals sigma times sigma inverse. That is the identity permutation. So they form a group. That's good. And then a representation of a group is just a matrix valued function. I'm running out of space, which is somewhat bad. So representation, these matrices which appear in the Fourier transform, are matrix valued functions. So they so rho sigma is going to be a, say, d-dimensional complex valued matrix, such that, and this is the crucial thing, that rho sigma 2 times rho sigma 1 equals sorry about that, rho sigma 2 sigma 1. Okay, so this just says that representation matrices mirror the group operation. So representation matrices are like a way of capturing this crazy structure of permutations by matrices. Okay, so I told you what representations are, and they're important because these are what go into our notion of Fourier transform. Okay, so this was the general part of the talk. Now let's try and connect that up with our multi-object tracking problem. Okay, so the main claim is going to be, I'm going to write down the Fourier transform formula again because it's going to be so crucial. So the main claim of the paper is that if you want to do something like maintain an approximate distribution over permutations, then the sensible thing to do that is to actually take its Fourier transform. So if f is the distribution, and then take its Fourier transform, which is again the sum over these representation matrices weighted by the function values, and then identify the low frequency Fourier components. So identify the low frequency matrices and just worry about those. So the claim is that we're going to be doing the same as we do in ordinary sort of signal processing, which is to just focus on the low frequency modes and throw away the high frequency components. Okay. And I'm going to motivate this now, show you that this might be sort of sensible thing by connecting it up to other sorts of things which you might do. Okay. So what is the simplest thing that you might do when you want to maintain association between objects and tracks? Well, the simplest thing might be to just have an n by n matrix, which in some sense gives you the marginal probabilities, right? So the AI entry of this matrix is going to be the probability that object A is actually at track I. This is like the first order approximation to this problem. It's clear that it's not the whole story because this is all just n squared numbers, and there are n factorial permutations, so you're losing a lot of the kind of higher order structure. But in actual fact, many of the practical systems in use just do this. But then you lose these higher order things like you might have constraints. So you might know that individually A might be at I and B might be at J, but the probability of it happening together for some reason, like they don't like each other or something, is 0. So then this sort of representation clearly just misses out completely on this sort of higher order information about your distribution. So what might you do? You might have higher order matrices capturing the second, third, kth order information. So just as you have, so you might realize that this comes from a hierarchy, right? This n by n matrix is the first order thing, but then you have an n squared by n squared matrix, or rather n times n minus 1 squared matrix, which contains these second order marginals of A being at I and B being at J. Or you might have third order stuff like that. But yes?
Fix the D in your seed. Is there a unique representation of the permutations? Or are there more representations for?
Yeah, so I was vague about these representations. The issue is that there is kind of a canonical set of representations for any group. So these are going to be, there's certainly not going to be just one representation. And in fact, if you have one, sorry?
There's a notion of equivalence you can transpose.
Exactly, there's a notion of equivalence up to unitary transformations. There's also a notion of reducibility, so representations might fall apart into direct sum of small representations. But what's important is a kind of maximal set of inequivalent, irreducible representations. And this is what, so there are descriptions of these. For the symmetric group, it was worked out 100 years ago, what these are. So these are going to be representations of different sizes. So it will tell you that there are two one-dimensional ones, and then there are two n-1 dimensional ones, and so on. There's this whole sequence. We're going to come back to that. There are several representations, but not an infinite number of them, definitely. All right. Wow, 15 minutes. Okay. 20. All right. Okay. So how does that relate to this sort of kth order approach? Well, the thing about the kth order approach is that there's a lot of redundancy in there. So even in the first order case, it's clear that there are constraints on this matrix. It's doubly stochastic, right? So each row and each column must sum to 1. So that puts, if I'm right, 2n-1 constraints on the matrix, which you can, if you implement that, that means that this matrix, by an appropriate unitary transformation, falls apart into this kind of block diagonal thing where you have an n-1 dimensional block and just something in the corner. Now, the same sort of thing happens with the higher order matrices as well. So in general, what we're going to see is that these higher order association matrices decompose in some sort of minimal block diagonal form by just a unitary transformation, or in fact an orthogonal transformation in our case. So from the point of view of doing this kth order thing, the interesting question is, how do I find this transformation, and what are these components going to be? Now, for the Fourier transform picture is good because it turns out that these things on the diagonal actually correspond to these different Fourier components, right? So in this case, for example, there's this one-dimensional one that's exactly going to correspond to the one-dimensional representation, and there's going to be an n-1 dimensional thing which corresponds to the next one, and so on. So this block structure, it's really fundamental to the nature of permutations, of how these matrices block diagonalize. That's going to be given to us by representation theory. All right. Now, a seemingly totally different thing is the worry about how errors occur in this, and what are the slow modes or the fast modes of these distributions with respect to the error process, right? So how do errors occur in multi-object tracking? Well, what happens is that if you look at it on a kind of fine-grained scale, so epsilon time differences, it's always just a first-order swap that happens, right? So you're maintaining the identities of these n objects, and with some probability in any delta t time interval, two of them are going to get swapped around. So you can visualize this on a graph. You have the different permutations. So you have the identity permutation 1, 2, 3, 4, 5 for 5 objects. This is going to be like one of your permutations. And then with some probability, you transition from this to 1, 2, 3, 5, 4. And with some probability, you transition to, say, 1, 5, 3, 4, 2, and so on. Okay? So this induces a graph on the set of permutations. It's called the Cayley graph, generated by transpositions, because in group theory language, these swaps are called transpositions. And then what you're interested in are the different eigenvectors of the graph Laplacian of this thing. That's going to give you the kind of slow modes of variation on this graph. So this is a nice connection to graph theory, and it's a sort of fashionable thing of graph Laplacians and diffusion kernels, whatnot, in machine learning these days. Now, you try and identify these slow modes, it turns out that what you get is exactly these different Fourier components. So the individual modes are going to correspond to individual components of particular Fourier matrices. So that's again the same thing. This is everything comes back to kind of the same tune. So there's a strong justification for using Fourier methods in multi-object tracking. Okay, so I don't need to go over this slide again. I already told you what the representations and what the Fourier transform look like. What I have not told you, of course, is how to actually compute them. And I don't think I'll get a chance to tell you in the remaining 10 minutes either. But I want to give you some kind of flavor of what happens here, in particular how to even enumerate the different representations, because those are going to tell you, what are the components that we are going to worry about. Well, it turns out that the canonical thing to do is to label those by these Tetris shapes called Young diagrams. So this is a Young diagram of with a total of 7 boxes. So it's going to be indexing one of these irreducible representations of the permutation group of 7 objects, and to enumerate the different possible irreducible representations, so the different Fourier components, you have to worry about how many of these things you can construct. So how many ways can you kind of lay down 7 boxes so that according to this rule that each of the rows must be left justified and no row can overhang the row above it and so on. So there's this natural sequence of these combinatorial objects, say starting with the horizontal one. So just 1, 2, 3, 4, 5, 6, so 7 boxes in a single row, and then one of the boxes can go into the second row. That's going to be the second representation, so that's going to be the second Fourier component, and then you need to worry about putting 2 boxes in the second row this way, or putting them in the second and the third row this way. So it's not clear exactly how many of them there are, but you can certainly enumerate all these possibilities. And then my approach to the multi-object tracking thing is going to be to identify those of these diagrams or those of these representations which we're interested in, and just cut off our scheme at a single point and say that is what I'm going to use to represent the distribution over permutations. Okay, and now there's more stuff. The next thing to worry about is, of course, how big are these matrices? So it's all right that we can now enumerate all the different Fourier components, but we still don't know how big they are going to be. And it turns out that's going to be given by how many ways you can fill these diagrams with the numbers 1 to n according to an extra rule that they must increase from left to right and top to bottom. So this is, again, a combinatorial type problem. I don't have time to go into this in great detail, but I can give you some sense of the whole scheme. So if you follow this prescription and just enumerate all the different representations, then it turns out that there's a neat order, and they kind of increase in size according to this rule. It's going to be a one-dimensional representation. Can you see these boxes, by the way? I realize that this might be a problem at the back. Okay. So there is going to be a one-dimensional Fourier component here. There's going to be an n-1 dimensional Fourier component indexed by this diagram. Going to be 2 Fourier components which are order n square dimensional, 3 which are n cubed dimensional, and so on. And if you follow through with either the graph Laplacian approach or the decomposition of kth order permutation matrices, it turns out that this is exactly the order in which you want to consider the different representation matrices. So basically, in the tracking case, you have a choice of either cutting this sequence off here after the first 2, which gives you an order, order n squared matrix, which turns out to be equivalent to the classical thing of just maintaining the first order marginals. Or you cut the sequence off here, which gives you second order information, or you cut it off here, which gives you third order information. So this is a clear prescription for how to do this. Okay, so So this slide just reiterates this, that we have a choice of we have this kind of tuning knob saying how much accuracy can we afford, whether we maintain the first two the first two Fourier components, the first four, the first seven, and then it kind of gets hopeless in practical applications. Now, not only do we want a parsimonious representation of the distribution, we also want to update this distribution, of course. So we need to worry about every single step of what you do with these things in a Bayesian filtering setting, right? So can we add noise? Can we do the prediction from time t to t plus 1? It turns out that this sort of scheme is really helpful in that regard, because adding this sort of random transpositions noise, so any two things being exchanged has the same probability, that just corresponds to convolution by a very simple function which has a diagonal Fourier transform, essentially just rescales the matrices. So this is almost free. So this business of considering all possible transpositions over all possible permutations, you can do straight in the Fourier domain without transforming back to the original domain. There's no worry about incurring n factorial n factorial cost. Now, the more interesting thing is, how do you do conditioning? So what if you actually have an observation? Say I consider observations of this form, that object A is at track I, but I have some uncertainty about this observation. So I say that with probability pi this happens, and 1 minus probability, and 1 minus pi probability it doesn't happen. How do I update our distribution in Fourier space with this sort of information? So this is the Bayesian update rule. Now, the key thing to notice here is that this kind of selects a very particular set of permutations, bumps up their probability, and bumps down the probability of everybody else. Okay? And this fits neatly into the scheme of fast Fourier transforms. So the reason that it's possible to do this without transforming entirely into the original space and incurring n factorial cost is because we know how to do fast Fourier transformation on non-commutative groups as well. Okay. So in 5 minutes, the idea here is very similar to the idea of the ordinary Cooley-Tukey fast Fourier transform. The idea is to take the original group and break it down into subgroups. So they just kind of divide and conquer thing. Say that the original fast Fourier transform can be composed of Fourier transforms over subgroups. In our case, the Fourier transform over permutations of n objects somehow reduces into Fourier transforms of permutations of n minus 1, that into n minus 2, and so on, all the way into the trivial Fourier transform over a single object. And this is the actual math. I was hoping to derive this for you on the board, but time is not going to allow me to do that. Let me just say that the crucial idea is, again, this decomposition decomposition of the Fourier transform over the entire group into a sum of Fourier transforms over the subgroup, right? So this is the crucial equation here, which kind of suggests this telescoping sum property, that you can decompose the full Fourier transform into n separate Fourier transforms over n minus 1. So this is the group that permutes just the first n minus 1 objects and leaves the last one in its original place, right? There's an extra representation matrix coming in, but otherwise it's a complete decomposition into, here it is even shown even more clearly, into the Fourier components over the subgroups. And it turns out that these different subgroups embedded in the full group, well, they correspond to exactly those sets of permutations which put the last object at a particular location. Okay? And this is the sort of observation you have, right? So when you observe something, when you have this I goes to n type of observation, that is one of these embedded subgroups called called a coset, which says that I don't know where everybody else is, but I know that the ith or the a object I is at track j. So since the fast Fourier transform is built on exactly this sort of decomposition, doing the Bayesian update is easy. It corresponds to not running the entire Fourier transform, which would have cost n factorial, but just running a part of it. So running it down kind of one level, and also not involving all the different Fourier components, just the ones that we are maintaining, which fit neatly into the scheme. And the morale of the story is that the whole thing can be done in let me write this on the board. So the expense of doing a single Bayesian update is going to be order d times n, where d is the size of the largest Fourier matrix which we're maintaining, right? So obviously d is going to, and our method is going to scale at least linearly with the number of data points, the number of components, with the number of real numbers that we're maintaining, but it's only an extra cost of n on top of that. So this is kind of viable in a practical setting, even for relatively large n. And code is available for it. So this is from my homepage. I coded this up in C++. The algorithms have been around for a long time, although people have not really thought much about how to specialize it to this kind of tracking setting. But apparently nobody has coded it up. So now you can download it and try it out for yourself and run it and so on. And finally, the inference step also falls neatly into the FFT framework and can also be done in this with this sort of cost, provided you are only interested in marginal probabilities. So computing the full distribution, of course, that's going to be expensive, right? So if you want to enumerate over something over n factorial possibilities, that's going to take a lot of time. But if you just want to, you're just asking yourself, what is the probability of object I being at track j? That's easy to do. Okay. So this is the data that we tried it out on. We culled this data from the internet because now you can find this sort of data like this is a real-time or just slightly delayed information about the actual positions of actual aircraft over New York. You can see the two main airports here, JFK and LaGuardia. And by adding a suitable amount of noise and throwing away all the aircraft labels, you really have this identity problem of who is who, aircraft cross tracks and so on. So the first thing that we wanted to check was that this hierarchy of Fourier decompositions really does hold. So having more Fourier components is supposed to help. And indeed, it does help. So I'm not sure if you see these plots clearly. But on the vertical axis, there's error. And the horizontal axis, there's the number of Fourier components we maintain. So these are intentionally small experiments with just 6 or 10 or 15 aircraft. But already the number of possibilities is quite substantial. So, of course, 720 permutations hold, like maintaining those explicitly is no problem. This is kind of just about within the limits of my desktop computer. But for n equals 15, you can't afford to keep an explicit representation of all n factorial representations in your computer. But if you vary the number of Fourier matrices that you maintain, the error more or less decreases monotonically. So this sort of compromise between computational expense and accuracy really does hold. The other thing we did was we compared with another fashionable algorithm, Shumich and Trun's information form data association filter, featured at MIPS 2 years ago, and found that in a particular regime, when there's lots of noise, so when identity really is the issue, we can do much better than they can. So again, I'm not sure you can see the scale here, but their algorithm, according to experiments, had, say, an error of about 19% in this case, with 6 examples already, whereas ours was down to, now I can't see it on the screen, maybe in that. So it was. I think this is just under 10%. So this is a significant improvement. Whereas here for They had a 28% error, which kind of matched our error for just the first two irreducible representations. But as we added more information, we could do much better than they could. And thanks to the fast Fourier transform, this whole thing is fast enough to do in real time. So it's really a matter of like 1 second updates or something like this. It could run on a real system. Great. So one nice thing was that soon after our paper came out, Huang, Gestrin, and Leo Gibas wrote a similar paper to NIPS, which used exactly the same representation. It turns out that they've been thinking about this for a while, but they also went a bit further because they allowed more general update rules, which gets messy. So it uses Clebsch-Gordon coefficients, which were difficult to compute in the first place, and that's expensive or not, but it really opens up the possibility of a much more general, flexible framework than we had. And also, they managed to do something which we had trouble with, and that is the ringing problem. As in ordinary Fourier analysis, we have exactly the same problem, that when we only maintain a few of the low-frequency Fourier components, then occasionally we're going to have negative probabilities, right? And that's really bad in any probabilistic framework. So they implement this trick by quadratic programming. They manage to project back onto the space of legal probability distributions. So there's more of this type of work coming out. Hopefully there's going to be even more. And it's going to be linked up with the general literature on fast Fourier transforms and non-commutative harmonic analysis and so on. All right, so let me just summarize. So the key idea here was that just as in ordinary Fourier analysis, you can talk about band-limited representations on non-commutative objects as well, say permutations. And this is kind of the canonical thing to do when you are dealing with the multi-object tracking problem or the identity management problem in the multi-object tracking framework in particular. And the whole thing hinges, so in practical sense, the whole thing hinges on being able to do these fast Fourier transforms. So we are really building very closely on that literature. Then the positivity constraints are a major concern, but there is some way of enforcing them, as discovered by Huang and others. And finally, you can probably sense that although I mainly talked about multi-object tracking, it's not really just about multi-object tracking, right? There's a more general story here about doing things on these non-commutative objects, finite groups, or even the general compact groups, and the usefulness of this thing, right? This weird type of matrix Fourier transform. Great, thank you very much.
I've got a sort of, I guess another way to do this would be to say, instead of at each time step in the HMM, you've got a n factorial states to consider. Basically what you could do is from the state transition from time t to time t plus 1 of those permutations, just consider a very small number of changes. So interchange 2 to transposition, or you've got the n squared of them, or 3 will be n cubed. So in that sense, I mean, it's not really, if we limit ourselves to the set of transitions which have got 2 or 3 transpositions, it's not an n factorial problem. And it's not, if I were to sort of say subsample that, so it's true that I get an observation here at time t, at time t plus 1, but I say that within those, I actually make a sort of a finer resolution where I say there could be some unobserved transpositions, but many of them, then each of them is still n squared, but it's got a Markovian property, so it still scales linearly with time. So that would be another way in which you could get, you could essentially enable to get many, get a sort of fake, basically, to switching the identity would have a linear time algorithm. Do you see what I mean? So
yeah, so
just by limiting the state space to those a relatively small number of updating states.
So the issue is when you do not get good identity information for a long amount of time.
Right.
Because eventually, so if at time t equals 0, you know what the right permutation is, then sure, at time t plus 1, you only have order n squared possibilities to consider. but then in the next moment you're going to have n to the 4 things to consider and so on. And here's the distinction between the different domains between identity management and data association and so on. So that and identity management, it is assumed that you might have these long stretches of time when you don't get any information about, say, a pair of guys. And there, this exponential blow up is something that thwarts all the approaches which rely on maintaining individual permutations. So just a matter of which domain you're working on. So the assumption is that you get information about the individual object separately. So you don't know, and you don't never get told where everybody is exactly. Maybe at time t0 you do, but later on you just get these snippets of information. Great, thank you.
Let's thank the speaker again.